Welcome to this video on vibration isolation for harmonic excitation. This video provides some extra material to the exercises of the course in machine dynamics. My name is Matthias Fischer and I am research assistant at the Institute of Engineering Mechanics at the Karlsruhe Institute of Technology. So let's start with the first example. You can find this example in the online material in the exercise of machine dynamics. Here we have a vehicle that is connected to the surrounding by a spring and by a damper, and we have a rotating mass m, a mass force excitation with the force mr omega squared. And we want to study the horizontal position of this vehicle, which is denoted by x. We can derive the equation of motion and find this form here, that we can also bring to the standard form by normalizing it and find the equivalent quantities. From the equation of motion, we can find the magnification factor and the phase shift of the system. And in order to better understand the magnification factor and the phase shift, we want to have a look on the animation on the next slide. In this animation, we will study what happens if we slowly increase the rotational speed, so the angular frequency. So we will move in this plot from the left to the right by increasing the excitation frequency, and the same for the bottom plot here. And in the top plot, we consider the magnification factor, and here we consider the phase shift. In this example and in the next examples, we don't consider a transient excitation, but we will also focus on what happens if we consider the angular frequency to be fixed at a certain point. So we start in the beginning with very low frequencies. We can see that the vehicle slowly moves, and it is in the beginning in phase with the excitation force. Now we pass through the resonant frequency with maximum amplitudes, and the amplitudes get lower until they reach a certain constant value for very high angular frequencies. And we can also see that the phases have switched. So in the beginning, we had an in-phase movement between the force and the vehicle. And in the end, for high angular frequencies, we had an antiphase between the force here and the movement of the vehicle. So I will play the animation again, and I will step out of the slides so you can have a closer look. So let's continue with the next example. In this example, we consider a 2 degrees of freedom system. So we have our first degree of freedom, the outer box here with mass 2m, and we have the inner mass point m with the position x2 with respect to the outer box here. And both masses are connected by a spring here, and the outer mass is also connected to the environment by a spring. And we consider a force excitation P, at the outer box, so at the first degree of freedom of the system. And we will later assume this force excitation to be a harmonic excitation. And we can find the equations of motion again, as you can find in the course material online as well. We can find the particular solutions for this given harmonic excitation here. And of course, we have two solutions because we have 2 degrees of freedom. And if you have a close look, you can see that we have the same denominator. And if we study the zeros of the denominator, we can find 2 angular frequencies. So these are the natural angular frequencies of the system and the resonant frequencies. But we see a difference between the numerators of the 2 solutions. Especially if you look at the first numerator here, you can see that for a certain omega, we find a 0 of the numerator, which is a characteristic of this tuned mass damper system. Because then we could add this additional mass m here in order to achieve the situation where we have a 0 amplitude of the outer box here. And we will see this in the animation as well. So in the animation, we will look at the magnification factors of the two coordinates, x1 and x2. And we see the resonant frequencies omega 1 and omega 2 here. And as I mentioned before, we have this point here where the amplitude of the outer mass becomes 0 while the inner mass is still moving. So let's start the animation. At the beginning, we have very low frequencies. We have a slow start of the movement of the outer box here. And if we increase the frequency, we can also see that the inner box with respect to the outer box moves. And now we have passed through the first resonant frequency. We have now an antiphase motion for both masses. And now the amplitude of the red box becomes very small, and it becomes 0, as you can see here. So this is the characteristic of this tuned mass damper system. Now we approach the second resonant frequency, where the amplitudes get very high again. So infinity. And now above this second resonant frequency, the amplitudes become lower again. And then you can also see that we have an in-phase motion here, so because of the positive value, and we have an antiphase motion here because of the negative value. So in-phase means that the blue mass point and the force move in phase, whereas the red box and the force are antiphase. So I will play the animation again and step out of the slide so you can have a closer look. So as we could see that the motion close to the resonance frequencies was quite unrealistic because we didn't include damping in the system. So the amplitudes become infinity, as we could see in the animation. And this is not realistic because every real system would have any damping in it. So the amplitudes would be limited in some sense. In order to study this in this example, we could also modify the example and include damping here. So instead of only having these springs here, we would also include dampers between the masses. And then we have a certain change of the amplitudes and of the phases. Again, we have the amplitudes for the resonant frequencies, which become quite high, not so high for the second one. And we have the characteristic frequency for the tuned mass damper, where the amplitude, the red curve of the outer mass, almost becomes zero. And we have a certain characteristic of the phase shift. Don't be confused because of the jump of the blue curve here. This is just the same value from pi to minus pi. So this is a smooth transition. And opposed to the last example, where we only considered the magnification factor, we now include the phase shift, because in the example before, we included positive and negative values here, whereas in this example, this is to be considered as the absolute value of the magnification factor. And before, positive value was associated with phase shift of 0 and a negative value associated with a phase shift of minus pi or plus pi. And in this example, we have not only 0 and pi as phase shifts, but we have some values in between. That's why we plot the phase shift as an additional curve here. So let's start the animation. Again, we start with slow motions, so with slow changes of this force here. We already observe some motion of the outer body, and after that also of the inner body with respect to the outer body. And we already observe a phase shift. We pass through the first resonant frequency with high amplitudes. Now we approach this tuned mass damper frequency here. So we observe that the amplitude of the outer box becomes very low, whereas the inner body is still moving. Then we approach the second resonant frequency, where the amplitudes become higher again, not so high as for the first one. And if we increase the frequency even further, we see that the amplitudes of both bodies slowly become smaller. And we see that, as before, we have an in-phase movement of the inner body. So the inner body moves in phase with the force, and the outer body moves anti-phase with the force, as you can see with the value pi here. So I start the animation again and step out of the slide so you can have a closer look. So this is the end of this video, and I thank you for your attention.